so curved mirrors today. We're going to start like we finished yesterday. So curved mirrors, there are 3 rules that we are going to follow. Let me put those up on screen for you all. You should have copied this into your notes yesterday in one version or another. This is the guide of how you will do these ray diagrams for curved mirrors. So make sure you have this in your notes. You should already. This was literally written on this board yesterday just like this. So if you don't, take a minute, get this scribbled into your notebook. You can copy it word for word or, I don't know, bullet points if you want to do it that way, whatever. But these are the way to be successful when drawing ray diagrams to predict the properties of images from objects with curved mirrors. All right, so let's find some open space. Here we go. Okay, so we are going to start like we ended yesterday. The mirror. And we are going to run this back. Okay, so we're going to start with a drawing that looks like this, where we have an object. I think in the book, the object that they use is a light bulb. I'm going to use arrows on here because this has an arrow making thingy. But just know that whatever this object is, this is the object that we're putting in the path of this mirror that we are trying to generate the image of this. What's this point here?
Focal point.
Focal point. This is a concave mirror. And this is our center line. So this is the basic setup of a curved mirror. So next, all we need to do is start following the rules. What is ray number 1?
Parallel to the center line.
Parallel to the center line. So this is going to come in and hit our mirror. And now again, this is directly from the Investigate that you did on Monday. How is this reflected ray going to look?
Through the focal point.
Okay, it's going to reflect back through the focal point. There are protractors on your desks if you would like to replicate these fancy straight lines that I am doing on the board. Not necessary, but it will help with what comes next. Also, as I go around the room, some of you are drawing these bigger or smaller than others. My recommendation is make these a little bit bigger. It's going to make tracing out all these rays that we put on these a little bit easier the bigger your drawing. Okay, so rule number 1 has been followed, or not rule, ray number 1. What about ray number 2? What do we do with that? Ray number 2? Yeah, so we'll get to that. I think you described rule number 3, but we're going to go to where the center line and the mirror intersect. And now how is this reflected ray going to reflect back?
Same angle.
Yeah, so the same angle. This is like we had rays with the plane mirrors. It's going to come back at more or less at the same angle that it went in at. And now, what is our third one going to be? So this one's the opposite of ray number 1, right? Where ray number 1 went parallel and then came back through the focal point. This time we're going to go through the focal point. And what will the reflected ray look like for this one?
Like the center.
Great.
Yeah, straight back, parallel to the center line. And if my art skills are good and accurate, you end up with these reflected rays converging at a point, and this is going to create our image. Again, we did this yesterday. This is when we held the thing out at arm's length. You guys have the mirrors at your desks if you want to try and prove me wrong. So we are going to define 3 properties of this image. First, is our image right side up or upside down? Upside down. You guys did this yesterday with the little mirrors, right? Looked like you, only upside down. So we're going to call that inverted. Inverted instead of upside down. Were you bigger or smaller in the image? Smaller. And does that match what you have drawn in your paper, what I have up here on the board? Yeah. This arrow is upside down, and this arrow is smaller than the object. And lastly, and this one's not going to make a lot of sense right now, but this is a real image. Of course it's real, Climber. But this is real because these rays are actually intersecting somewhere. If you held up an index card at that point, you would be able to see the image. They are projected. Those rays actually focus in somewhere. They actually hit together. And again, that seems like I'm just making stuff up. It's going to make sense 5 minutes from now. And again, we did this yesterday. This is no different than the other set you probably have in your notes already. So take a minute, make sure you've got this figured out, you understand the rules that we just did. Let's keep going. Draw another setup. What is different about this configuration?
Way closer.
Yeah, so the object is closer to the mirror. It's inside of what? Yeah, this one's actually inside of the focal point. We did this yesterday as well. You have the mirror in front of you to do this. You can make a concave mirror. You can put it right up to your eyeball. So let's start making some incident rays. So what's our first one?
Parallel to the center line.
Okay. How is this going to reflect?
Through the focal point.
Through the focal point. Now, yes, technically that's going through the object itself. For a moment, just trust. Okay, so this is no different than what we did 5 minutes ago. First ray goes to the mirror, reflects back through the focal point. Okay? Ray number 2.
Same angle.
Intersection.
Okay,
On the center
here we go. How is that going to reflect? Okay, congruent angle, same angle. Okay. So far, so good? This is starting to look a little different. What do we all of a sudden not have that we had before? An intersection. So let's all hold on tight here. What is our third example ray going to look like? Through the focal point. Now wait a minute. Focal point is behind our object. We still want something to hit the mirror. We want a third reference ray. But you're right, if we just draw it like this one's not going to hit the mirror. Right? It's going backwards. We want something that's going to hit the mirror. Well, how do we do that? We need a reference line. We need to know what that line is. Don't draw this in your notes quite yet. So if I connect our object and our focal point, that's what this dotted line is. Now all this is for is just so I can aim my ray. I want to draw a third reference ray, but I need to know where to aim it. And I'm going to aim it along the same line that connects that spot on the object that we're using, the top of the object, and the focal point. And then I'm going to shoot a ray at that spot. Now, what do we know about our third ray? It is in the same line as the focal point. What does ray number 3 do when it hits the surface? It reflects in what direction? Parallel. So it's going to reflect back this way. And now, for the sake of cleaning this up, I'm going to get rid of that reference line. And now again, none of this is magical. This is just rays reflecting off of a mirror, depending on what input angle you put it at. But what is the problem with these 3 reflected rays?
They don't touch.
They don't cross. What if I zoom out? Will they cross someday, somewhere down the line?
Probably.
No.
Think geometry here.
No.
Are those 3 going to intersect somewhere off to the left somewhere? No. However, what if we went the other way with these 3 rays? What if we went through the mirror? They would, but not in reality. So we are going to leave reality. Several of you have done this before already. So what you need to do here is take your reflected rays and carry them through the mirror. What does that look like? Well, for this particular reflected ray, you just carry it backward through the mirror. You do this for all 3 of your reflected rays once you've drawn them. Guess what? They do. There is an intersection. And again, this is where it gets a little weird. It's not real. Now, this forms an image. You can see this with your eyes. Specifically with your little test mirrors, like if you hold it up to your eye, right? Hold it real close so that your object is inside of the focal length, you can actually see this. So our image in this case doesn't make sense is the correct answer. Like I said, this is weird. But But all this means is you can see this image, but you're only seeing where these things would connect. But there's no actual, like, you couldn't put an index card up and get an image. You couldn't project this somewhere. But let's define our three things about this image. Our properties. Number one, is this image right side up or upside down? Right side up. Upright. Is this image bigger or smaller?
Bigger.
Bigger. And now here is, this is not real. In this, we call this virtual. Is the word. Imaginary. And now again, anyone that has used a makeup mirror knows what this is. You get right up close to a makeup mirror, it magnifies your face or whatever you're doing. And you're upright. It would be not very useful if your makeup mirror had you upside down. It would make everything really hard to, be really hard to do. So this is what happens when your object is inside of your focal point in a concave mirror. You get this situation. And again, you just have to kind of trust in the rules that we've put together to get this answer. Now, another thing that kind of is difficult about this is all these lines, keeping them straight. Sometimes one line is a little bit wonky, it doesn't line up. Again, depending on how you drew this, where you put your focal point, and how curved the mirror is, this can kind of get difficult to draw. The next one we do will probably break my ability to keep this straight. Everybody got this? See what we're doing here? Let's make it weird.
We're doing the opposite this time.
Concave.
Just asking.
So to answer your question, this is now the other type of curved mirror. What would we call this kind of mirror?
Convex.
Convex. Now, luckily, we have the same three rules. We need to label a focal point. Where is the focal point going to be here, though?
On the other side.
Yeah, on the other side of the mirror. So let's draw our rays. What is our first ray going to look like?
Parallel to the center line.
Parallel to the center line. All right, so intuitively, now you guys did this. This was in the Investigate on Monday. You got to play with lasers and actually do this. Where is this reflected ray going to reflect off? In what general direction?
Back at you.
Straight back?
No.
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 Straight through.
No. It's going to burn a hole in the mirror.
Go straight.
Straight up?
Not like straight up, like
Like
even.
up.
Yeah, so it's going to be, it's going to be up here somewhere, right? Well, let's not guess. What was our rule for ray number one if it comes in parallel?
Reflect the focal point.
Reflects through the focal point. Is it going to go down this way through the mirror? No. But the focal point is going to inform how this ray reflects. We need another guide point. We need another guideline. it is going to reflect along this same line, the same pathway. So our reflected ray is indeed going to go through the focal point, but kind of not really. It's going to go like this. And again, this should look like what you did on Monday. You might have this in your notes, in your information from your investigate. I don't remember what number. So now that I have this, I'm going to erase my guideline. Okay, what's our second ray?
Intersection.
Okay. Now, luckily, this one is a little easier. Do we know where this one's going to go? Yep. So this one is actually normal, sensical, whatever, symmetrical. So line number 2, super easy. Now, what about line number 3? Yeah, we're probably going to need another line, but what is the definition of line 3 or the instructions for line 3? Through the focal point. Are we going to be able to draw it all the way in through the focal point? No. So I'm going to do another test line just so I know where this is going to go. And again, how you choose to do this on your paper, I have the luxury of erasing a thing. You could just kind of trace it along this line. So my real ray is going to come in here like this. And now a ray that's drawn on the same line as the focal point, how is it going to reflect? Parallel. So let's see what that looks like. It's going to be like this, right? Then I'm going to erase my test line. So I have my 3 reflected rays. We did this one first, and then this one, and then this one. Now, once again, here in the real world, are those 3 rays ever going to converge somewhere? No, one of them spins off up, one of them comes straight back, and one of them goes downward. So these things are never going to converge. So what should we do instead? Yeah, let's carry them through the other way in the virtual space. Now this is where, as many times as I've ever done this, I can never get these to actually intersect properly, but we're gonna change that today, right? No, that's not the one. We have this reflected ray. Wait a minute. I may have done it. You hate to see it. We did it, team. All right, so where do these intersect?
Right in the middle.
Not the middle.
Above the center line.
Okay, so we're going to have an up arrow here. There's a convergence point behind the mirror somewhere. So here is our image. Let's define our properties of this image. Upright or inverted? Upright, I agree. Number 2, bigger or smaller? Smaller, I tend to agree. And lastly, is this a real or a virtual image? Virtual. It's behind the mirror. All right, so I scavenged a convex mirror from the electricity unit. We'll get there someday, I promise. Here is a convex mirror. How do you all look in this mirror? I know it's weird. For starters, are you upright or inverted?
Upright.
You're upright, right? If you can see yourself in this mirror, I know it's not a polished, very good mirror, but are you upright or inverted?
Upright.
Upright, right side up. Are you bigger or smaller?
Smaller.
Are you sure?
You're smaller.
Still bigger or smaller?
Smaller.
Still bigger or smaller?
Smaller. Bigger.
So here's the beauty of convex mirrors. What you see up here will hold true, boys. What you see up here will hold true for all convex mirrors. If you've ever been to the Bean in Chicago, right, what can you see in the Bean in Chicago? Yourself, what else?
All the people around.
Yeah, all the people around, what else?
Your feet.
I mean, yes, your feet, but what else?
The top of your head. Well, it's like
The sky and the floor.
Here we go, the sky, all the buildings in Chicago. You guys have been to the Bean, right?
Yes.
Okay, so yes, all of you is in the Bean, sure. But all of Chicago is also in the Bean. Even the big giant buildings behind you all look smaller, but they're all still straight up and down. Right? That is, most parts of that Bean are a convex mirror. There is, like, if you crawl underneath it or whatever. Remember, don't touch the Bean.
Why? It's nasty.
It's gross.
That's a dog.
Yeah, everybody in Chicago touches that thing, and the TikTok challenge was probably awful. All right, so don't do that. Go observe, check out a giant convex mirror. It's fascinating, but don't touch it, and if you do, wash your hands immediately.
What if you like Windex? Before
Like clean a certain, just a small portion? Maybe. Maybe.
But who really wants to touch?
I don't hate that, but like so many people have, it's kind of gross. All right, so here's where we go from here. These are the basics of drawing a ray diagram for you to predict what an image will look like based on where an object is and what kind of curved mirror we're talking about. And for the sake of this class, we're only talking about basic convex and concave mirrors. Next week, we will add in the math that is under the hood of all this, where you can actually say, okay, I have an object, it's 8 centimeters high, it's located this far away from the mirror, the focal point is this, where will the image be? And again, you'll have to both describe the properties of the image, then also say, oh, it's inverted, it's 4 centimeters tall, and so on and so forth. So it's important that you understand the fundamentals now on how you draw it so you can kind of predict your answer, right? If you're working with a convex mirror, let's say, and your object is 20 centimeters high, and you do all the math, and you come out with your object is 80 centimeters high, can that possibly be true? No, because everything, the images in a convex mirror are going to be smaller. So your ability to wrestle through the fundamentals here will help inform you when we actually do the math next week. Any questions on this stuff? All right.